All right, continuing with our A-level curriculum for Computer Science 9618, we'll be talking about topic 15.2, which is flip-flops. Let's dive into the learning targets. We need to show an understanding of flip-flop, both the SR and the JK flip-flop. We need to draw a logic circuit and derive a truth table for a flip-flop. We will do that today. We'll also understand the role of flip-flops as data storage elements. So what is a flip-flop? Well, there's two types of logic circuits. Now in AS, we talked about the first one, which is known as a combinational circuit. The output is dependent only on the inputs. You have the inputs A, B, C, whatever they may be. You combine them, you throw them through some gates, and you get a 1 or a 0. Now this year in A-level, we talk about what is known as a sequential circuit, which is the second one. The output depends on the input value produced from a previous output value. Well, what does that actually mean? Well, this is a combinational circuit. There's no feedback here. Nothing new that we've seen. We have inputs A and B. We throw it through an AND gate. We take this input, which is an output, throw it through a NOT gate, and we get our final output. It's only the inputs that determine the output. There's nothing going back into something else. Now in a sequential circuit, we have an animation here. I found this online, so thank you to whoever made that. So here we can see Q is being fed back into S. It goes through this NOR gate, and then the value of not Q is being fed back into R. That produces the value of Q, which is being fed back into S. We get not Q, and it feeds back in there. So this is a flip-flop. There is a flip-flop in a sequential circuit. Notice Q is feeding into S, not Q is feeding into R. And that is a sequential circuit. That is a flip-flop. So the first flip-flop is known as an SR flip-flop. Now the SR stands for set reset, and it's what we call an active high or active low. So maybe your professor or teacher has said, well, SR can be active high or active low. Well, how in the world are you supposed to know? Well, it's dependent upon the gates that you use. Using NOR gates, we call it an active high because one of the outputs has to be high. Well, that means it needs to be a 1. In order for it to work, one of them has to be a 1. Using NAND gates, it's what we call an active low, which means one of them has to be 0. And of course, we're going to look both of these. We're not just going to throw the truth table and say, yeah, just memorize this. We're about understanding. I need you to understand. I want you to understand. I want you to be successful. No matter what question is thrown at you, you'll be able to answer it and get those points on the Cambridge exam. So, before we start, we simply need to quickly review OR gates. Remember the rule for an OR gate? As long as at least one value is true or high, we get a true value. Here I have A and B are both 0. Neither one of them is true, so that gives me a 0. A or B, B is true, that gives me a 1. Here, A is true, that gives me a 1. But what about if both of them are true? Well, the rule is as long as at least one is true, you get a true value. Now, we're going to be using a NOR gate, which is a OR gate followed by a NOT gate and an inverter. So let's say we have 0 and 0. So 0 and 0 going through an OR gate give me 0. And I'm going to try not to keep clicking that pin. We get 0 here, but then we hit that inverter. What's the inversion of 0? And that is 1. So that's how we get these. And all we're doing really is inverting this output right here. These ones have become zeros. If I have 1 and 1, so just quickly explaining and reviewing here. If I have A is 1, B is 1, going through an OR gate, that gives me 1. But then I hit this inverter, and this inverter inverts it to 0. So that's how I got that there. All right, so let's talk about the purpose, and then we'll get into drawing those logic circuits for the flip-flops. So it's used for memory. The memory stores a 1 or 0, and this shows 1-bit memory because it's either a 1 or a 0. It's used in shift registers in a computer. Also can be used as a binary counter if you link several of them together. Now, the reason you're probably here is for this. Now, let's start with NOR gates. We said earlier, it's active high. This means in order for it to reset or set, it needs to be set to 1. What are we resetting and setting? We're resetting or setting what is known as a latch. So if you hear people talking about setting the latch, they're talking about a set reset positive feedback or sequential circuit. So we're going to walk through these both being low and high so we can understand how it actually works. So let's take a look at this. So we have R0, S is 0, not Q is 0, and not Q is 1. Now we've had people say when both inputs are 0, Q and not Q do not change. Well, that's nice to know, but we need to understand it. We need to see why it does not change. So let's start with R. Not Q is 1. I bring that up here. 0 or 1 gives me 1. I hit this inverter and I get 0. This 0 is brought down here. I have 0 or 0. We hit the inverter and that gives me the value of 1. So Q and not Q did not change. The value of Q is 0. The value of not Q is 1. But what if both of these are 0 and we have 1 at Q and not Q at 0? Does it stay the same? Because people will say, well, they can also have this state, but let's understand why it can have this state. Let's start with S. Doesn't really matter which one you start with. So we'll bring this 1 down. 1 or 0 equals 1. We hit this inverter, it becomes 0. 0 or 0 come out to 0. We hit this inverter and we get a 1. So we can see right away by running this and understanding it why the values of Q and not Q do not change. So when R, the reset, the S set, when they are both at 0, the value of Q and not Q do not change, which is why they can have this starting state or it can have this starting state. So where Q is 0 and not Q is 1, or it can have Q is 1 and not Q is 0. All right, so R stands for reset. When R is active high, Q should reset to 0 and not Q should become 1. Because Q and not Q, they cannot be the same number. If Q is 1, not Q must be 0. If not Q is 1, Q must be 0. They both cannot be 1. They both cannot be 0. They are complements of one another. All right, so let's start with R. So I'm going to bring up this 0. 1 or 0 gives me 1. But remember, I hit that inverter. That means this 1 becomes a 0. Well, that gets positive feedback fed back into S. So we have 0 or 0, which gives me 0. I hit this inverter and it becomes a 1. Now you might be saying, well, hold on here. This is 0. If this is being fed back in, how does it stay 0? Well, let's go ahead and run it. Let's change this. This is being fed back in to 1. 1 or 1, give me 1. I hit this inverter, which is still 0. I carry this 0 down. 0 or 0, give me 0. We hit that inverter, and it's a 1. So it still is in a balanced state. It still works. Now, because R stands for reset and it's active high, when R is 1, it's going to reset the latch, meaning Q becomes 0, not Q becomes 1. But what happens if Q is already set at 0 and R is set to 1? What happens then? Well, let's go ahead and run it. We'll run S this time for kicks. 0 or 0, give me 0. I invert that, it becomes a 1. 1 or 1 gives me 1. I invert that, and it becomes a 0. Now you might be saying, well, what if I run R first? Well, let's go ahead and run R first. Let's go ahead and do that. It doesn't matter which one you run because it should balance out if you're doing it correctly. It's very easy to make a mistake on these, and I'm probably going to click that many more times. All right, so I bring up the 1. 1 or 1 gives me 1. I invert that, it becomes 0. 0 or 0 gives me 0. I invert that, and it becomes a 1. So it stays in the reset state with Q being 0, not Q being 1, because R stands for reset, which means when it's a 1, Q is going to become 0, not Q is going to become 1. Now, S stands for set. So what happens when it is set to 1? So this time we have S is 1. We're starting with Q at 0, not Q at 1. Well, if we're setting the latch, Q should become 1. Let's see if that happens. So I bring this 0 down here. 0 or 1, give me 1. 1 inverted becomes 0. So far looking pretty good. 0 or 0, give me 0. We invert that, and it becomes a 1. Now you might be saying, well, hold on. We had a 0 down here. Let's go ahead. Let's feed it back in here. Let's change this 0 to a 1 because now Q is a 1. Well, if I feed that into S, 1 or 1 still gives me the value of 1. We hit that inverter, it becomes a 0. The 0 gets fed back into R. It is in a stable state. It will always have this. The latch has been set. It has been set to 1. Q set to 1. But what if S is set to 1? And what if R is set to 1? What if we're trying to set and reset at the same time? Is that even possible? Well, it's a scenario, so let's go through it. Let's try S. So bring down the Q. 1 over 1 gives me 1. I hit that inverter, comes out to 0. Well, okay, so far so good. All right, hit this R. 1 over 0 gives me 1. I hit that inverter, that gives me 0. Well, Q and not Q cannot be 0. Well, you know what? Maybe it's not balanced. Let's go ahead and update it. So let's change this 1 to a 0 because now Q is 0. 1 over 0 give me 1. I invert that and it becomes 0. Carry that 0 up. 1 over 0 give me 1. Hit the invert and that's 0. This is not working. Well, it's not supposed to work. And this is the downfall of an SR latch. So this is the truth table. Now, we said when they're both set to high, 1 and 1, we have what's called an invalid state. They're both going to have the value of 0. That is not possible because Q and not Q must be complements of one another. Whichever one is 1, the other one must be 0. Whichever one is 0, the other one must be 1. When we have, this is not two different rows here, this is the same row. And remember, we said there are two different starting states. When S and R are both 0, the value of Q and not Q do not change. So this actually counts as one row. When we have R set to 1 because it's active high, it should reset the latch, meaning Q becomes 0, not Q becomes 1. When S is 1 and R is 0, we are setting the latch, which means Q becomes 1, not Q becomes 0. When both of them are active high, we have what's called an invalid state. So let's use Nand Gates and see if we can overcome that problem. Now we said earlier Nand Gates are active low. This means in order for it to reset or set, it needs to be set to 0. We're going to walk through these, S being low, R being high, R being low, S being high, so we can understand how it works. Now, what you need to notice here is that we are not using NOR gates, we are using a NAND gate. Both of these are NAND gates. And also notice that S is now at the top, R is at the bottom. And it does matter. You cannot just say, well, it doesn't really matter which one's on the top because they're both going through NAND gates. Yes, it does. In this one, S is corresponding to Q. R is corresponding to not Q. If we go back to the NOR gates, R was corresponding to Q, S was corresponding to not Q. So it's important to remember that. When you're using NAND gates, S corresponds to Q, R corresponds to not Q. All right, so let's jump in. So what if S is 1 and R is 0, with Q being 1 and not Q being 0? What will happen if the setup is active low? Will it set or reset? Well, if it's active low, R should be happening. R should control what happens, and R stands for reset. If this works like it should, Q should become 0, not Q should become 1. So let's see if this works. So we'll start with R. So we have 1 and 0. Going through an AND gate, that gets me 0, but then I hit this inverter, this not Q becomes a 1. I bring this 1 up here. 1 and 1 give me 1. But I hit this inverter and it gets me 0. Well, you might be saying again, well, what about this 1? Now it's 0. Fine, change it to a 0. 0 and 0 still give me 0. I hit that inverter, it gives me a 1. It is in a balanced state. Well, what if Q is 0 and not Q is 1? Now, we're still going to have the same condition where S is 1 and R is 0. Will we get the same result? Will we get 0 and 1 like we did if it's already in the state, or will it change? The only way to find out is to run it. So let's do this 0 and 0. This 0 and 0, that gives me 0, but I hit this inverter, which gives me this 1. I carry this 1 up here. 1 and 1 give me 1. Hits this inverter, which is a 0. that 0 I've already brought down, so it all works out. So yes, it stays the same. R stands for reset. Using NAND gates, it's active low. Because R is 0, is active low, it's going to be in the reset state, which means Q is 0, not Q is 1. Now, let's try now with S being low and R being high. We will start with Q being 0 and not Q being 1. Let's find out what will happen. And we can ask ourselves, will it set or reset if this setup is active low? So we can start with S. We bring up this 1. 0 and 1 give me a 0. I hit this inverter. This becomes a 1. Bring this 1 down here. 1 and 1 give me 1. So make sure we were on, yeah, here we go. 1 and 1 give me 1. I hit this inverter, and that changes this to 0. If you're worried about this up here, that's fine. Get rid of this 1, put a 0. 0 and 0 still give me 0. Hitting this inverter still gives me a 1 because it's active low, and S in this scenario is low because we're using NAND gates. It will set the latch, making Q1, not Q0. All right, let me get rid of this down here because I did not mean to write that. Okay, keeping the same setup with S being low and R being high, let's flip the value of Q and not Q. Q is going to be 1, not Q is going to be 0. Will it set or reset if the setup's active low? Because this is another possibility. Just for kicks, let's run R first this time. It doesn't matter which one you run. 1 and 1 becomes 1. We hit the inverter, we get 0. 0 and 0 give me 0. I hit the inverter, which is 1. So it stays inside the set state. Now, what if they're both active low? Does that fix our invalid state? Because that's why we tried setting it up with NAND gates, was to see if it'll fix the invalid state. Well, let's investigate. Let's go ahead and do S first. So 0 and 0, that gives me 0, which gives me 1. Nice. So I bring this 1 down. 1 and 0. Give me 0, which gives me 1. Well, let me get rid of this 0 here because the 1 may balance it out. 0 and 1 give me 0. I hit this inverter, which leaves me with 1. If I bring this 1 down, 1 and 0 give me 0. I invert that 0, gives me a 1. Did we mess up here? No, we didn't. That is the downfall of an SR latch, regardless of whether you use NOR gates or if you use NAND gates. The difference here is when both of them are set to 0, we get an invalid state. When both of them are set to 0, the output is 1. They both cannot be 1. That is the invalid state. So the truth table works a little differently. When both of them are 0, we get an invalid state. In a NOR gate, when both of them are 0, we got a valid state. So for this one, it's a little different, but you can make your truth table based on all the scenarios that we have here. So invalid states. So how does this work if both logic circuits create invalid states? It doesn't work at all. Jack Kilby came up with a solution, and it's called the JK flip-flop. The JK flip-flop fix the invalid states. So we're going to take a look at the JK flip-flop. It's called the JK because of Jack Kilby. So here we go. The JK flip-flop. Now notice, this looks complex, and it's really not. And there I am clicking that button again, and we need it to, come off. There we go. Finally. Oh boy. Okay, here we go. So this right here is my SR latch. All we did was tack on 2 NAND gates at the very beginning. That's all we did. That's all we did. And one more thing, we added a clock pulse. So when we talk about the clock cycle of the computer, that's every time that it does a pulse. Now, let's go ahead and start it. Let's start with J being 0. So I'm going to do J is 0. K being 0. So I'll fill that out. Q being 1. Not Q is going to be 0. We're going to find out what's going to happen when both J and K are set to 0. So clock pulse is always going to be 1. When you see the clock pulse, it's always going to be 1. We'll start with J. J is being fed the value of not Q, which is 0. So running that through an AND gate, that gets me 0. I hit the inverter, which is 1. Bring up this 0. 1 and 0 give me 0. I hit the inverter, which gives me 1. I'll go ahead and bring that 1 down here. That 1 is Q. It's being fed back into K. 0 and 1, 1 give me 0. But remember, I'm going to hit this inverter, which is going to give me 1. 1 and 1 give me 1. Hitting the inverter becomes 0. That 0 is carried back up. It is in a balanced state. So what happens is when J and K are both 0, Q is 1, not Q is 0. So it does not change, or in this case, it did not change. All right, the clock pulse is always going to be 1. But what if J is 0, K is 0, but this time Q is 0 and not Q is 1? What's going to happen here? So let's go ahead and run J first. It doesn't really matter. You can keep running it till it balances out. My clock pulse is always going to be 1. So we run 0, 1, 1 through an AND gate. That gives us 0. We hit the inverter, which is 1. Bring up this 1. 1 and 1 give me 1, but I hit this inverter, which gives me 0. I bring that 0 down. This 0 gets fed into K. That is what we call positive feedback. This gives me 0. Hit the inverter. That gives me 1. 1 and 0 give me 0. Hit the inverter, and it gets me 1. So what happens here when we look at this first one and the second one, when J and K are both 0, the values of Q and not Q do not change. They do not flip. Because here we started with 1, we started with 0, we ended with Q being 1, not Q being 0. Here we started with Q being 0, not Q being 1, and it stayed the same. So when the values of J and K are the same, or I'm sorry, excuse me, when they are both 0, Q and not Q remain the same. Now, let's start with J being 1. Let's start with K being 0. Clock pulse is always going to be 1. And we're going to set Q to 1 and not Q to 0. So let's go ahead and run J, bringing not Q around. And when you're looking at these AND gates, you can work through them pretty quick, but it's very easy to make a mistake. So make sure you're not making a mistake. 1 and 0. In order for this to be 1, they all three have to be 1, but they're not. So it's 0. But don't forget, we hit this inverter, which becomes a 1. I bring up this 0. 1 and 0 give me 0. I hit this inverter, which gives me a 1. I bring that 1 down. Now, we can do K. This is going to give me a 0. I hit the inverter, which gives me a 1. 1 and 1 give me 1, but I hit this inverter, which is a 0, and it works out. We are done. So when J is 1 and K is 0, is it Q stays the same, or is it Q becomes 1? Well, the only way to answer that question is to do the same thing, but this time looking where Q is 0 and not Q is 1. So I'm going to feed not Q into here. Now, we have 1, 1, and 1. The clock pulse is 1, J is 1, not Q is 1. This gives us 1. We invert it, which gives us 0. I bring up the 1. 0 and 1 give me 0, which changes this to a 1. So I bring down the 1 here. Now, the clock pulse is 1, K is 0, Q is 1. So running 1 and 0, that gives me 0. I hit the inverter, which gives me 1. 1 and 1 is 1, which makes this 0. So now that we've run this and we're in a balanced state, it works. Now you may be saying, well, what about the 0? What if I bring it up here? Well, go ahead and bring it up here. 0 and 0 still come out to 0, and we still get 1. So it stays in a balanced state. So what happens here, when we look at it, when J is 1 and K is 0, Q becomes 1. J is the set. K is the reset. So let's check that and let's make sure that's what's happening. So let's set J to 0. Clock pulse is always going to be 1. K is going to be 1 here. And we have Q is going to be 0. Not Q is going to be 1. All right, let's run J first. It doesn't really matter. So we have 1, 0, 1, and 1. Give me 0. I hit this inverter, which is 1. I bring up that 1. 1 and 1 give me 1. I hit the inverter, which gives me 0. Then I do K. The value is 0 because it remained unchanged here. So 1, 1, and 0 give me 0. Hit this inverter. This becomes a 1. 0 and 1 give me 0. I hit the inverter, which gives me 1. We are in a balanced state. So K, because it's active, it is resetting the value of Q to 0, not Q to 1. But what if J is 0, K is 1, and Q is 1, and not Q is 0? What if we have it different this time? Will we still get the same result? And I think by this point, you should start knowing if we're going to get the same result. So we can go ahead and run J. 0, this is going to give me 0 because not all three of them are true. We hit the inverter, which gives me 1. We get 0 here. 1 and 0 give me 0, which gives me 1. I bring it down. We have all three ones here. This gives me 1. Hit the inverter, which gives me 0. 1 and 0 give me 0. This gives me 1. Oh man, did we mess up here? Well, let's just go ahead and keep working it, because what's going to happen is this one gets fed in here. So this 1 and 1 give me 1. This 1 inverted gives me 0. This 0 comes down. 0 and 0 give me 0. When I invert that 0, it becomes a 1. Well, if I bring this 1 back up, it's going to stay the same. So it is now in a balanced state, and that is why I said earlier in this podcast, it does not matter which one you run first. You may be saying, well, my God, both of them are 1. Well, let's see if it balances itself out, and it does. It comes out to what we call a balanced state. Now, what if J and K are both 1? So Q is going to be 0, not Q is going to be 1. So we'll do J first, just because that's what we've been doing. Like I said, and what we just proved earlier is it doesn't matter. So 1, 1, and 1 gives me 1. I hit this inverter, which is 0. 0 and 1 give me 0. That means this Q changes to a 1. I'm going to bring this 1 down here. So I have 1, 1, and 1. This gives me a 1. Hit the inverter, which is 0. 0 and 1, and I'll make this clear as we know this is a 1. 0 and 1 give me 0, which gives me a 1. If I bring this 1 up here, 1 and 0 give me 0, which gives me a 1. I bring this 1 down here, 1 and 0 give me a 0, which gives me a 1. So what happens here? And this is the importance of filling this out correctly. So we did this to prove a point here, and we're going to run J again and show you something here. So the clock pulse is 1, J is 1, Q is 0, not Q is 1. We're going to bring this 1 around, and we're going to have the clock pulse K. The Q value of K is 0. Let's see if we get something different here. So because we cannot, this should fix the state. So having all 1s gives me 1. We invert that. It becomes a 0. 0 and 1 give me 0. We invert that. That changes Q to 1. I bring that 1 down here. This time by having 1, 1, 0, by loading the previous Q value, this comes out to 0. We invert this, which gives me the value of 0, which gives me a 1. 1 and 1 is 1. We invert that, which becomes a 0. If I bring this 0 up here, 0 and 0 still give me 0. We invert that, becomes a 1, and that gets carried down. When you are loading the value of Q into K or the value of not Q into J, you must load what it is at the start. That way it will run. Because you may be saying, well, hold on, what does it matter? Well, when the clock pulses, it runs them. They're not going to run at the same time. One will run faster than the other, and whichever one runs first depends on how the circuit's going to go, but it's always going to come out into this state. So here we had 0 and 1, or we have 1 and 0. We started with 0 and 1, but we wound up with Q being 1 and not Q being 0. Does this mean it's setting, or does this mean it's toggling? So Let's do J as 1, K as 1. This time we're going to do Q as 1. We're going to do not Q as 0. And you want to load those, initial values here. All right, let's run J. 1 and 1, 0. That gives me 0. I hit this inverter, which is a 1. I bring up that 0. 1 and 0 give me 0, which gives me a 1. Going to go ahead and bring that down here. 1 and 1 give me a 1. I hit this inverter, it becomes a 0. 0 and 1 give me 0. I hit the inverter, this makes it a 1. Now, before you start freaking out, let's just see if this thing balances itself out. So this 1 gets carried up here. This 1 and 1 gives me a 1. I hit the inverter, this gives me a 0. I bring this 0 down here. 0 and 0 give me a 0. I hit the inverter, which becomes a 1. If I bring that 1 up here, 1 and 1 give me a 1. I invert it, it becomes a 0. We are in a balanced state. And this is why I say you want to keep running to see if it balances itself out. And the last one, we didn't load it properly, which is why we got, I think, 1 and 1 or 0 and 0 to begin with. So you want to load the initial state of Q into K, the initial state of not Q into J, and then run it. That is very important to know. So looking here, we have the starting value of Q and not Q. We said when J and K are both 0, Q and not Q remain unchanged. So here, the final value of Q would be 0. The final value of not Q would be 1. And you can go back and we ran all of these. So if you'd like to rewind, feel free to do so. I encourage you to do so. It's all about understanding. When J and K are both 0, the starting value of Q was 1. The ending value is 1. The starting value of not Q is 0. The final value of not Q is 0, because the rule is when both J and K are set to 0, Q and not Q remain unchanged. Now the clock pulse is always going to be 1. You're always going to see it written as 1, or and if you're in another class, you may see it written like this, some kind of symbol, meaning it's running. But it's always going to be 1 in Cambridge. So what about when J is 1? When J is 1 and K is 0, we said it becomes set. So Q becomes 1, not Q becomes 0. So here, if the starting value is 0, it becomes 1, not Q becomes 0. And then we have, well, what about K? And we said K is like the reset. If K is 1 and J is 0, Q becomes 0 and not Q becomes 1. And we can see there are two scenarios where that happened here. These two scenarios, Q becomes 0, not Q becomes 1. And then in the final state, what if both of them are 1? What that means is Q and not Q toggle. So if Q was 0, it becomes a 1. If not Q is 1, it becomes a 0. In the other scenario, if Q is 1, the final value becomes 0. If the starting value of not Q is 0, it becomes a value of 1. And just like that, we have our JK flip-flop, our SR flip-flop, our sequential circuits, our truth tables. We have everything we need. If you have any questions, please post a comment below. We will see you guys in the next video. Right after we do these, because this is the summary of the truth table. You can jot these down. This will make it super easy. When both J and K are set to 0, Q and not Q remain unchanged. If J is 1 and K is 0, Q becomes 1 and not Q becomes 0. J is the set. If K is 1 and J is 0, then Q becomes 0, not Q becomes 1. K is the reset. We're resetting that state. And then if J is 1 and K is 1, then the value of Q and not Q is toggled, meaning they switch values. Now we have reached the end of the video. If you have any questions, please post a comment below. I do read them. If you have any questions, please post a comment below. I am here to help you if you need help. We'll see you guys in the next video.